But if I did the same chart for alcohol instead of water, specifically ethanol, let's do methanol. I know ethanol, so let's just do ethanol. So ethanol is a much smaller, it's still a small molecule. It's, don't quote me on this, I'm pretty sure I'm right, but looks something like this. Could someone look up the structure of ethanol on their phones? I'm pretty sure it's something like this. And so it seems like it's wrong somehow. Let me see. I have to look it up because I should know. It's easy. Is that right?
Yeah, that's about right.
All right, good. It's simple, so I was hoping I got it right.
Oh, the O and the H are separate.
Yeah, I think that's a matter of convention. Give me a second. Yeah, that's fine. So yeah, the O and A, there's a way of writing it. Like if I wanted to write it, like you could write it like this, like I just wrote it. It's as a hydroxide group because this is a functional group. One of the functional groups called hydroxide. So I could draw it out like this, and I could just say this is hydroxide, right? So this hydroxide is going to be very special. So you should get to know it now. All right, so this thing is called hydroxide, and it's very special. Anytime you see an OH, a hydrogen, you have a potential for hydrogen bonding, and that's really, so this OH is hydroxide. It's a functional group. Obviously, water has OH in it. And you know that OH can form, a hydroxide is in pH, right? It's a base. It defines a base. In this case, it's attached, and alcohol is it's kind of one of those molecules that's in between. It's much less polar than water. Water's much more polar. And here's an interesting thing. If I did the phase change chart for alcohol, here's what would happen. Yeah, I'm trying to draw a line. Oops, I did it again. Sorry. I'm trying to get this line drawn right by hand, and I don't want to mess you up. So what's interesting is now what is it down here? It's a solid. What is it up here? It's a liquid. And here it's a gas. Now, interestingly, ethanol is not as polar as water. And what do you notice about ethanol? Alcohol does not freeze at 0 degrees. There's dust in the air. It's in my throat. Can we focus? What is ethanol when it's a solid, when it's frozen? The temperature is much lower than 0 degrees. So it doesn't freeze at 0 degrees. You can put ethanol in your freezer. If it's 0 degrees, water will freeze, but not ethanol. Interesting. And when we get to here, look at here. Have you ever put ethanol, rubbing alcohol on your arm? Yeah. What do you notice? Okay. Let's assume it's not on a cut. It can dry you out. You will get ashy. You're right. But what is it? How does it feel? Cool, right? It feels very cool. That's because the alcohol will start to evaporate very quickly. its evaporation point's only 70 degrees, not 100. It's 70 degrees, not 100. So that's one. And two, it freezes much lower at a much lower temperature. And three, the energy required to make it change phase is a lot less. So it changes phase, this amount of heat required to change phase is much less. It's only a little bit of energy required to make it change phase. And its temperature, its freezing point and melting point, and its boiling point and condensation point, right? They're much lower than water. So the reason is that there's no hydrogen bonding, or very little hydrogen bonding with ethanol. So you don't have hydrogen bonding because it's not as polar a molecule, so you don't have as much hydrogen bonding, so there's not as much pull for the molecules towards each other. So it takes less energy to separate them. And it doesn't take that much kinetic energy to make them turn into a gas and start moving again. So that's really key. Now there's another, we can look at, now this is a polar molecule here. This is polar. This is nonpolar. And it's not nonpolar, it's kind of in between. Let's say less polar. And then you have a molecule that's nonpolar. I'm going to pick a molecule that everybody's ear is familiar with, oxygen gas. You breathe it in every day, you need it to live. Oxygen gas is just this. Completely nonpolar. This is if I did the electron dot, it would look like that. It's just a very, very small molecule like water, 2 instead of 3. And I have to look this up because I don't know. I'm sorry, this is 2. There's 2, that means 2 oxygens, right? And this is a gas, a G for gas. I'll look something up really quick. It's on a good periodic table. So oxygen, if I did the same chart for oxygen, there's 0 degrees. And I wanted to go from a solid, I wanted to freeze oxygen. Oxygen would be frozen at negative 218 degrees. So oxygen only becomes a solid at negative 218 degrees Celsius. So this is when it would stay a solid down here, and this is when it would start to change into a liquid, and then you could start to increase the temperature again, and then it would boil. Oxygen boils at negative 183 degrees. So oxygen becomes a gas at negative 183 degrees, and then oxygen stays a gas, right? So when you're taking a look at boiling points, at nonpolar molecules, it turns out nonpolar molecules have very much lower boiling points, much lower melting points than polar molecules. And I think it kind of supports the idea that polar molecules attract each other and nonpolar molecules don't. So nonpolar molecules don't attract each other as much. Let's say it that way. They do attract each other. There's these things called London dispersion forces, but we're not going to get into that. But when you look at nonpolar molecules, they don't attract each other as much. And what that translates into is that your boiling point is at negative 183. Water boils at negative 183 degrees. So oxygen, not water. So oxygen is you never see liquid oxygen in a room, right? You never see solid oxygen. You don't see a cube of oxygen gas, right? You don't see oxygen, the molecular oxygen in a cube. It's a solid cube. That wouldn't happen on Earth. Now you can freeze it, and you can turn it into liquid, like the tanks in that you go diving with, right? How do you do that? How would you turn it into a liquid without having it, and keep it from, on the surface of the earth? How could you do that? I'm going to give you one clue: the ninja. Yeah. You compress it. You can just add pressure, and now that gas will turn into a liquid. Not because what you're doing is you're literally shoving them together. Like taking two magnets that are resisting being put together, you can push them together, right? So if you compress it, you can force it to turn into a liquid, and then you can force it to turn into gas. But by the way, when you do that, it gets real cold. Have you seen that canned air? Who's seen canned air? I wasted it shoot. I had a can of air beginning of the year, and I messed around and I showed kids how it blows out of the can. What happens when you have canned air? You've never seen canned air? You saw it? You saw me doing that at the beginning of the year? Yeah. When I was scaring people with the sound. It's canned air. That's air that's been compressed. What happened to the can? Those of you that saw me do it, what happened to the can? Well, hopefully it doesn't explode. Jesus, God help us. No, because it can, but that would be a bad thing. That's why you never put any kind of spray can in a fire. Don't do that. It'll explode. Bad things will happen. Gases will be released. It's just horrible. So the bottom line is, you take did anybody see me spray the canned air in the beginning of the year? What happened to the outside of that can?
I don't have to that question, but I was asking, is dry ice kind of like?
That's a great question. I'm going to pull that. I'll put that on the screen real quick just to talk about that. But dry ice is a really good question. Dry ice is a crazy molecule. It's carbon dioxide. By the way, dry ice is just carbon dioxide. But it's not ice at all. There's no water in it. So let's be clear on that. So what happens when you do these crazy compressions and then decompressions, it gets really cold. When you release that gas, all that energy is going into, so let me be very clear. When you take this gas, and you can do it with oxygen, it'll be the same thing. It might be a little colder or warmer, I'm not sure. You take it and you shove it in a can. I ordered new tips because this tip is too. It's a can. And it's spraying out air. It's not as good as I'd like. The tip of my pencil is very slippery on the screen. I ordered a pencil that has a tip that has a little more grip, so I can draw straighter lines, because I either have to draw it straight. But anyways, this can is letting out the compressed air, and it's going to go out, and it goes from liquid, that's liquid in here, into a gas. When that happens, it has to get energy. It has to get energy. Where's the energy coming from? Good guess. That's really a good idea. I bet you there is some energy coming from that pressure on the knob. But the energy is coming from the surrounding area. If you're holding the can, it's coming from your hand. If you're not holding the can, it's coming from the air. So energy has to go in here. So energy's going in here. The heat energy's going in there. Well, how's that going to feel if you're touching this? How's that going to feel if you're touching that? If the energy's going in, it's going to be cold because you're losing heat. Heat's going out from your hand or from the air into the can. That energy is going to turn that liquid into a gas. It's going to literally suck the energy out from around it. And what you'll see if you ever spray air, the outside of the can gets very cold. Actually, ice starts to form on the outside because there's water in the air, and it gets so cold that the water in the air freezes onto the can. I'm going to bring in a can so I can prove it to you. All right, you can't spray canned air into people's eyes because it's very cold, and that could hurt their eyes. It could freeze their eyes. All right, this stuff gets very cold. You can spray in the air. Obviously, it's safe to spray in the air. It's just not safe to spray into people's faces, on their skins. Are we all clear on that? So if you ever see someone with a spray can, never point it at their face or at skin. But you can spray it obviously into a machine. That's what it's for, is to clean out keyboards and electronics. So anyways, it gets really cold and energy goes in. It goes from liquid to gas. And so every time you change phase, you have to add energy to make it go into one phase or take energy away in the case of condensation, right? Why does it rain? Because there's water in the air. In warm air, there's water. Relatively warm air, there's water. And then it gets cold. What happens? The energy's leaving the water molecules. What's going to happen to the water molecules? They're going to go from gas to liquid because they're cooling off. When they're warm, enough kinetic energy, they're gas. When you start cooling it off, they become liquid. So it's all about energy, heat energy, and you can tell that nonpolar molecules have much lower boiling points and freezing points because they don't have as much attraction. Water is just one of those really interesting molecules because it's 3 atoms, and it has a very high boiling point, 100 degrees, relatively high boiling point, relatively high freezing point for a molecule that size. As you can tell, the difference between oxygen and water, negative 218 versus 0. That's a big deal. Yeah.
Okay, so back to when you was talking about scuba diving, do the cans get like, when you breathe, do the cans get colder as you do it? Since the pressure is it like the same?
You mean as you spray it?
No, not as you spray it, like for scuba diving. For scuba divers.
Oh, good question. Scuba divers have a regulator, and you're right, that would be a concern. But the can itself, the scuba diving tank, is very thick metal. And when you're scuba diving, you generally are using it in a tank of water. And so it gets the energy from the surrounding area. But you're right, they do get cold. If you ever touch in fact, you don't even need to scuba dive. You know, they have those tanks in hospitals. Oxygen tanks, you've seen them? Oxygen tanks is this. They took oxygen and made it into liquid. But those tanks are very thick, so they don't allow the energy to be sucked out from the area around them because they don't want patients to get burned from the cold. So what they'll do is they'll have a regulator that'll change it and let it seep in. But if you've ever used those oxygen tanks, the gas itself, even after it's gone through the regulator and it's gone through the tube, it's still a little cold. It's never warm because it's gone through that process of condensing. Okay. So, and by the way, it's also how fast it happens. Like you don't want to release all that liquid gas into the air really quick because and also that's why liquid nitrogen is so cold, right? Because liquid nitrogen actually freezes much even lower, at a lower temperature, and so when it goes from liquid from liquid to gas, it freezes everything. Carbon dioxide, what we call dry ice, never turns into liquid. It goes from solid, this is CO2, not water, from solid right to gas. Also a nonpolar molecule, and it goes from solid to gas, no liquid. It's called sublimation. And that little white smoke that you see is not carbon dioxide. That's water. That's water in the air that's condensing into like a fog. All right. So this is called sublimation, and frozen or solid carbon dioxide, and we call it dry ice, sublimates and never melts, never turns into liquid. That little phase change for going from solid to liquid, this space between freezing point or melting point and boiling point is very small, so small you don't even notice it. So we call that sublimation, a special property of some gases. And it's not the CO2 dry ice is not the only one that does this, but there are. It's the most famous one. We use dry ice to keep ice cream cold. And we call it dry ice because it looks like ice, but it's not ice, okay?
Because it don't turn into a liquid, so it's dry and then it's gas.
And that's why they call it dry, because it never turns into liquid, that's right. It goes from solid to liquid to gas right away. That's why they call it dry ice. But it's not ice. It's not solid water. It's solid carbon dioxide. All right. So that, hopefully you have those drawn. Hopefully you have the main ideas, right? So if I drew these graphs in my notes and I were writing a summary, so what are some of the main ideas? Can you help me write some of the main ideas for these notes? So what would we title this page of the notes? What would we title this? Can we title it phase change?
Yeah.
Phase change energy. And there's a lot of important stuff we talked about. So what were some of the things that you might have written down? What stuff have you written down in your notes? Everything on the board is fine, but that we talked about a lot of stuff that we didn't write on the board. So what would you have written down if you were trying to write down something that was important? Yeah.
Non-polar molecules don't attract each other.
That's right. Non-polar molecules don't attract each other as much. And so that leads to lower boiling points and lower melting points. Remember, boiling points are also condensation points, so it's boiling point / condensation point, melting point / freezing point. All depends on which direction you're going. So polar versus non-polar. Kind of main idea there. A little reducing. I reduced all this content. I reduced it down to this. Polar versus non-polar. All right. What else might we've gotten from all this that might help us in biology? Yeah. Ethanol. All right, so ethanol is an example. That's good. So as an example, i.e. ethanol, less polar, equals lower freezing point, lower boiling point. It's freezing point versus melting point, boiling point versus condensation point. Anything else that we could have gotten out of this? So something that can be a summary or a question you might want to write as your summary. I wonder if things that are gas at room temperature and pressure, because we have to concern ourselves with pressure, right? We looked at pressure cookers, and that's a big deal. And we looked at oxygen tanks and nitrogen tanks and dry ice. So we know pressure has something to do with this phase change stuff. So I wonder if things that are gas at room temperature and pressure are non-polar. And if that's your question, if that's your summary question that you wrote, I'm going to give you your summary answer. Yes. Gases tend to be at room temperature. So they tend to be non-polar. So that makes sense. So oxygen that you breathe in, nitrogen that you breathe in, carbon dioxide that you breathe in and out of your mouth, air, is nonpolar. The things that are liquid at room temperature tend to be polar, or at least somewhat more polar. Not all true, not always. There are some organics that are liquid at room temperature for other reasons, other type of intermolecular bonds. All right, so I hope that helped. And tomorrow's Wednesday. Hold on, before you go. I know you got to go, but listen. Tomorrow we're going to go over the lab. Try to be on time. I understand the lines are long, so we have to deal with that. If you're going to be consistently late, we have to have a conversation. I am posting the lessons online. You should join the YouTube channel. You'll get it. As soon as you get it, you can watch it. You can catch up for anything you missed when you're late. All right, have a good day.